head-to-head overlapping of atomic orbitals. So in order to understand this bond, first we need to review what are atomic orbitals. Do you know what are atomic orbitals?
Yeah, is it like I can show you you know can I draw on the thingy
Yeah, you can draw on the screen.
like something like this,
Yeah,
and
got
then
it.
when
So how do you define
uh,
it? These are the shapes
define,
what you're drawing.
I don't know how to define them.
So basically, the understanding is that atomic orbital is a place, is a region around an atom where the probability of finding an electron is maximum. Now, first, the idea what I want you to learn and understand is that basically speaking, when when you realize what an electron is, so few of the authors and few of the scientists they believe that electron was kind of a particle, right? So then the research started that where do you find this particle? So few of the experiments in early centuries they led us to think that this electron particle is in a shell, right? And then we kind of used to draw an atom like a nucleus and then orbit, right? And then we have drawn electron like this. So that was way earlier discarded in the late 19th century because there was this concept which stated electron is not a particle, it is a wave. So when you identify a wave, you cannot identify an exact location of it. You cannot say, a wave is only at a certain point because what a wave kind of, is a vibration that oscillates in a region, right? It is in a complete different zone. It cannot be at a single point. It is spread out in a region. So to understand this concept, what you need to visualize is just think, uh, the way I used to explain this to my student was first I, asked this question with them that who are you more afraid of in your family? Is this your mom or dad?
Um, Probably mom, I think.
Okay. So if I treat you like an electron, okay, so it would be very, understood if you are, more afraid of your mom that you won't be found very close to your mom at your house. Do you understand this? Don't take it, too hard. Just this helps in understanding. Because, for example, if I am afraid of my mom, I would try to be as far as away in the next room, in my corner, in my office, because I am afraid of her. Do you get this?
Yes.
So, the presence of mom is kind of a field, a wave in the house where that, wherever that wave is, I'm going to go away from that. Do you get it?
Yeah.
So if I say, for example, that uh, had I been, an electron, and if I'm, let's say afraid of my mom, so I would be kind of in a region, or, if someone comes to my house and if he wants to look for me, he wants to meet me, he should, you know, probably meet me where my mom is not present. Do you get this? For example, if I'm calling on some of my friends, right? So I'm going to invite them outside my house. Why? Because I don't want my friends, meeting to happen when I'm afraid. Do you get this part?
Yeah.
So when you define an electron as a wave, you cannot define it in a point. You have to define it in a complete region. So for example, if I'm afraid of a certain teacher in my school, I'm going to avoid that teacher and the entire floor whichever she is, or the entire office room whichever she sits, because I'm afraid of that teacher. Do you get that point? So the presence of that teacher is going to be felt in a whole area. It won't be like at a certain point, because whenever that particular teacher observes me, she kinds of or he kinds of come up with, what are you doing, why is this happening, you haven't done this, you haven't done that. Do you get that?
Yeah.
Okay. So
So how does
when we define an atomic orbital, what we mean is that if you try to find an electron, if you try to locate an electron, if you try to search for an electron, so electron can be found in a complete region around a nucleus. You cannot exactly pinpoint it to a specific area. All this shaded area can contain an electron. So this entity becomes the s orbital, the spherical orbital. Do you get this?
can so wait, can you explain it again? Like,
Yeah. So let's say, when I say that electron is not a particle, that is really important to understand. A particle can be anything which is present at a single location. For example, let's discuss you. Right now, you're sitting in your home, right? So the only place where I can find you is your home. You get this? You're
yeah,
now absent from your college or from your school. But
yeah,
once you are in your school, you can only be found in a particular room in a school, right?
yeah,
But your presence becomes absent from your home once you're in a school, and your presence becomes absent from your school once you're at home. So you can be present only at a single point. Do you get this?
yeah, yeah, yeah,
Because we humans, we are particles. We are particles, right? Now,
yeah.
for example, I'll give you this, kind of another example to understand this. So let's say this is, a building, or this is a house we live in, right? So that's me. That's my room. Okay? So if some of my friend, comes here at the door and he searches for me in my room, or sorry, in my house where I live in, the only point he can find me is here. Is that correct?
Yes.
So I cannot be present everywhere. I'm only present
No.
at a specific point.
Yeah.
You get this?
Yes.
But that is true for particles, because we are particles, we are not energy waves. Particles are
Mm,
present at a single point. You get it?
yes.
Now, let's say, you know, if this is me in my home and I am doing, anything in my room which I don't want others to see. Okay? For example, I'm sleeping. For example, I'm singing. For example, I'm dancing. For example, I'm eating something which everyone in my family likes. You get it? So just think and answer this. I am hiding from all the persons on my in my house, right? But I cannot hide from angels, jinns, fairies, Allah Ta'ala, and things like those. You get it?
Yeah.
So
Yes.
just think, this is more like metamorphical. Just think that, can I minus those things out by keeping my doors shut?
No.
No. So they are everywhere, right?
Yeah.
You understand this? They're everywhere because they're not particles. They're energies, they're energy waves. My angels can
Mm,
see me through walls, right? The jinn outside my room is going to see me doing anything. Allah Ta'ala can see me from everywhere. Do you get it?
Yeah.
So idea here is because those substances are not particles. They're not like us. So they can see us doing everything. Is this understood?
Yeah.
So if I want you to think that okay, now Rumesa think where are exactly your angels? So would you be saying, okay, sir, one angel is sitting on my right shoulder and the other, angel is sitting on my left shoulder, and the one on my left shoulder is always writing things about me, and my, right one is just relaxing and chilling because there is nothing good to write. So is that actually happening, or is that they are meant to be a concept so that we are always conscious that we have to do right things, we have to do good things because all that is being good conducted by us is recorded. Just think.
Yes.
So kind of, there is no home on my right shoulder, right? There is no chair on my left shoulder as well. So this is meant for us to understand that there is some energy. There are angels. We are not denying them, but we are saying that they are in a location where they can see always, where we cannot do anything absently from those angels. Everything that's done is rewarded. You get it?
Yeah.
So when I say think of a wave, I mean you to feel an energy. So that energy, despite being not there, is always there. Do you get it?
Yeah.
So in my room, I cannot see Allah Ta'ala. I cannot see the angels, but they're there, right?
Yes.
Do you get it?
Yes.
So
So
when
it's the same
scientists they
like
say when scientists they say electron is a wave, they meant is that electron is spread it around a nucleus everywhere. Do you get it?
yes.
So that is s orbital. If the spread of an electron is somewhat spherical, right? You know that the s orbital shape is spherical. You know that.
Yes.
So
Yeah.
now we can also move to that p orbital, which you have tried to draw. So that is again a region, uh, area where we can find what? Where we can try to find an electron in a p orbital. So if there is a high energy orbital, that's p orbital. So we draw it like this, maybe along x-axis, maybe along y-axis, and maybe along z-axis. We get this? So all this specifies that we can find an electron everywhere here in these lines. So it becomes a wave. We can find it everywhere. Do you get it?
Yes.
Do you now understand it?
Yep.
Now we have to, complicate a bit things. When we say they're going to bond, they're going to be attracted to each other. That's really important. So, for example, this is an s orbital, right? And that's another s orbital. So if they kind of bond, so what happens is they fuse, they melt. I'm just using terms so that it stays very simpler for you to understand. So they're going to fuse like this, and they're going to form something like this. So now I'm going to say that in the first s orbital, where was an electron? So electron was somewhere supposed to be here, right? And in the second s orbital, where was an electron? So electron was somewhere supposed to be here, right?
Yeah.
So that is an atomic form in which they are not bonded to anything, but here they're being bonded. So where are the electrons? These electrons are going to be here. But the difference between these electrons and the electrons we had initially is these are now associated to a molecule. These were all atoms. Do you get it?
Yep.
So what you essentially understand, what you should understand through a sigma bond is two things. They kind of absolutely fused together. melted together. They had a head-on collision, and then they are, kind of connected together. So I explain it like this in my class. Let's exemplify that I'm having two clay balls. Do you know what clay is? The students,
Yeah.
the thing which we, used to play in our childhood. So just
Yeah.
imagine two clay balls, and then you roll them up and you bring them closer, and you just apply sufficient force so that they fuse. Do you get it?
Yeah.
So whenever they fuse, they actually touch, they actually, go into one another, and they actually join across the axis. Is this understood?
Yes.
So this is what is going to form a sigma bond.
Okay.
So if we are studying a sigma bond for carbon, let's say, so if I'm saying that, we are having an s orbital here, and we are having an s orbital here for both our carbon atoms, so they're actually going to fuse like this. So this is going to be, the bonded region. Do you get it?
Yeah.
Is it
That's the
understood?
same example you gave up above, right?
Yeah. Yeah.
Okay.
You get it? Are you sure?
Yeah. Yeah. Yeah.
Okay. Just give me a minute. I have to remove these. I don't know why is that not going on. Um, um, okay. Okay, that's nice. That's nice. Now, coming towards the other side, now, what is a pi bond? So how do you understand what a pi bond is? So what do we mean by, a pi bond? So
It has a dumbbell shape.
So basically, a pi bond doesn't have a dumbbell shape. Pi bond is a bond that is formed between two atoms which are already bonded by sigma bond, and it is formed sideways, not headways. Okay. So what does that has to mean? So let's say this was a carbon atom, right? It has this p orbital, the dumbbell shape orbital, and it has, 3p orbital. Let's draw, for example, for simplicity just. So this is another p orbital of carbon, and these two carbon atoms are going to form a bond. Okay, so these are dumbbell shaped p orbitals.
It is already.
Do you
Wait, what?
understand this?
Sigma bonds and is formed sideways, not headways. Like, but then there's like this headways as well, right?
What does that has to mean?
Like when you said something like this. I'm not
This is, yeah, this is a p orbital. This is not a bond.
P. So you're talking about pi bond. Okay, okay.
Yeah. So p orbital is something else. Pi bond is something else. So when you draw
V2.
something like this, you mean p orbital. When you draw something like this, you mean s orbital. Okay.
So the one orbital is sigma bond.
No, every orbital can make a sigma bond. Let's move on. You just have to wait. So if they kind of decide to bond together, this part and this part, so they can
Yeah.
form a head-on collision, right? And this would be fusion or melting, right? And that's the sigma bond. So this is going to form something like this. So this region is what? The merger of these two, and that's a sigma bond. Do you get it?
Yes.
But there is one more thing. When you bring these, just think what I'm saying. When you bring these two carbon atoms too close, so these have been merged, right?
Yeah.
So they have formed this. So what happens to these? Think. What happens to
They
these?
they don't merge.
Yeah, but they can, kind of touch from this side and this side, right? And this side and this side. Why? Because these two carbon atoms are now very closer to each other. Let me show it to you. So it can
They
be
can.
something like this. Can be something like this. They are going to touch one another like this. It kind of feels an attraction towards the other. So what you should now think is that that was the p orbital, and this p orbital is bending or tilting towards the other p orbital. So they cannot merge head on, but they can be contacted, connected to a sideways or a parallel bond can be formed. That's a pi bond.
Okay. So still they're gonna have a. Oh, okay. So when something is sideways, it's pi bond, and something that is like um head to head is sigma bond.
Yeah, that's nice. Do you get it?
Yeah.
Are you sure?
Yes.
So the that is going to be very very funny example which I give. So for example, there are two friends, right? So these two friends are they're good friends in school. They're good friends always. So if they plan to sit on in their class, so what arrangement should they follow? Just answer that.
Sitting together.
Sitting together, right? So they can sit
Yeah.
together. So that's a sigma bond because they're sitting together. Do you get it?
Yes.
Just
Yeah.
imagine if they're sitting and they're holding their hands. That is going to be sigma and pi. Do you get it?
Because they're sitting together, so it's
The
sigma bond, and
Yeah,
it's
that's the
because
collision. Yeah, because they are contacted through the furniture, through the chairs, the arrangement of the classroom. They are sitting next to each other. That's the head-on collision. Because if one wants to move, other has to be moving, other has to move and all. So they are going to sit together, right? But if they're holding their hands as well, so that's the further connectivity. So that's a pi bond. Do you get it?
yeah.
Are you sure?
Yep.
So there is a difference in sigma and pi. Sigma is meant to head on. Pi is a sideways parallel. Do you get it?
Yes.
Are you
Also,
sure?
so
Yeah.
alkenes don't have, right? Only
Sorry.
alkenes have this.
Ev-
Alkanes don't have.
every bond, every covalent bond, regardless of organic, inorganic, can be a sigma and a pi. First,
Okay.
clear this understanding. We are not supposed to think that this is going to happen only in alkene. Why? Because alkanes they do form sigma bond. They don't have a double bond. Yeah, but sigma bond is there. So if we are talking about carbon dioxide, that is not to be discussed in organic chemistry, but carbon dioxide has double bonds. So it has pi bonds and sigma bonds. So everything can have a sigma bond and a pi bond. It's not specific to only alkanes and alkenes.
Okay.
Okay. Now let's discuss, what do we mean when we say a sigma bond? So sigma bond is going to be a first covalent bond, the way you define it. And after that has been formed, whatever is extra is a pi bond. So if I say, let's say I'm discussing a bond between H and H. So is this a single covalent bond?
Yes.
So that is going to be which bond? Sigma
S-
bond.
yeah,
Do you
sigma.
get it?
Yeah.
If I'm saying that we are having fluorine to fluorine bond, is this a single covalent bond? Answer is yes, that is going to be a sigma bond. If we are discussing, let's say, an oxygen to oxygen bond, so there are two bonds, right? So one of this has to sigma, one of this has to be pi.
Mm.
If we are discussing carbon to carbon bonds, so one of the bonds has to be sigma, one of the bonds has to be pi. They
Pi.
cannot both be sigma, they cannot both be pi. And
Okay.
things they don't stop. They go on. For example, if we are discussing NH, N2, for example, so that is going to be a triple covalent bond, right?
Yeah.
So one of the bonds is going to be sigma, remaining two are going to be pi.
Mm.
Do you get it?
Yeah.
So regardless of alkane, alkene, alkyne, carboxylic, aldehyde, ketone, it can be sigma and pi.
Okay.
So you just need to know that sigma is considered sigma because of head-to-head collision. Pi is going to
Yeah.
be pi because of already bonded with sigma bond.
Okay.
Any questions?
No.
Okay, that's nice. Now we can, start discussing what an alkene is. So alkenes are unsaturated hydrocarbons. Now, what is an unsaturated hydrocarbon? A hydrocarbon whose carbon is not fully occupied.
Can you not say carbon carbon double bond?
Yeah, that is what it would be. So if carbon to carbon double bond is present, this carbon and this carbon is not fully occupied, they can even make one more bond. So that's making them unsaturated. Do you get it? Do you get it?
Yeah, yeah. I got it.
Okay. Then the general molecular formula is CnH2n, and then they have this bromine test through which we can identify that we are talking about an alkene. Now, what that bromine test is? Do you know what that is?
Yeah, you add bromine water, and if the color changes from orange to colorless, then alkene is present.
So it decolorizes an alkene
Yeah.
and there is no change in alkane. That's wonderful. Do you understand it?
Yeah.
There is also KMNO4 test. KMNO4 does the same. It changes from violet to colorless in alkene and it changes no color in alkane.
Oh,
Do you get it?
oh. Yeah.
That's now. How are alkenes prepared?
Um.
Have you done it?
Yeah. Yeah.
Okay, let's go through it. How are alkenes prepared?
Fractional distillation.
No.
Alkenes are. It, can Well, I think I know it, but wait. Uh, can you give like a hint so I can remember?
What type of hint shall I give you? Do you know how are alkanes prepared?
Yeah, like
How was
fractional
it?
distillation.
No.
Uh, that's for crude oil, yeah.
Fractional distillation. Who told you that fractional distillation is a preparation method? Who told
But
you that?
what's the
That would be the question. Yeah.
no?
Who
Like,
told you
what
this?
is
Well,
fractional
yeah.
distillation,
So
reforming, and
it is
cracking
never
used
a
for?
preparation method. It is a separation technique.
Oh, okay. I always get confused between this.
I remember your same answer was there for alkenes. Sir, alkanes are prepared through fractional distillation. Now I'm asking you same question. How are alkanes prepared? He did that.
And then I don't know.
So we did alkanes, right? So you've forgotten that? I'm just asking a question which we already did.
But we never studied about the preparation of alkanes.
Are you sure?
Mm, I don't remember. I'm not sure though.
You have my slides for alkane.
Yeah.
Can you download it? Can you see it if there is something written on it?
Mm. Oh, is it because of the free radical substitution and stuff?
Have you downloaded my slides? Have you opened that up for
Yeah.
alkane? Do you
Yes.
find anything written preparation of alkane?
No.
You don't find anything relevant to it?
Oh, I did. I did.
And
All
what's that?
alkanes are prepared through same methods, cracking.
Now you know how are alkanes prepared?
Yeah. But then they also say if you want to separate them, you can also like, do fractional distillation, reforming or cracking.
Who who says that alkanes are separated through fractional distillation?
So like alkanes are used as fuels and can be obtained from fractional distillation, cracking and reforming of crude oil. It's written in
Yes,
my book.
yes, yes,
Yeah.
we can say
Is
that.
this right?
Yeah, this was what I was absorbing, but they are never prepared through fractional distillation.
Okay.
They
So they are
can be
only
obtained. So
prepared by
what
cracking.
you need to understand, yeah, what you need to understand is when we drill crude oil, it comes up to the surface. It needs to go through a lot of processes, and in that crude oil, we can have alkane. We can have alkane. We can have methane. We can have ethane out of that, right? So it's already there. We are not preparing it. Do you know what I just said? It's there. We are not preparing it. We are just separating it.
Breaking. Okay.
Separating it. We are just separating it. So let me give you an example. Can we separate salt from seawater? What would your answer be?
Salt from steam water?
Seawater. Seawater.
No.
Answer is yes, we can separate it. Industries, they do it all the time. So, we are not preparing salt from seawater. We are separating it. Salt was
Yeah.
already there. We are just collecting water. We are separating water and salt. So, are we preparing salt? No, we are separating it.
Okay.
So, if you separate out anything, you're not preparing it.
What about cracking? You're
So yeah,
breaking it.
that's preparation of an alkane. So we can have something non-alkane like diesel, like paraffin. That's not an alkane. That has a lot of double bonds, triple bonds things. And then we crack it. We do a chemical reaction. Cracking is a chemical reaction, and it converts to an alkane. So we are making an alkane.
Okay.
So for example, if I'm neutralizing an acid and an alkali, right? So am I preparing salt,
Acid and wait, what?
acid, and an alkali? Am I preparing salt?
Yeah.
So, am I separating salt from acid or an alkali, or am I preparing salt from acid and an alkali?
Preparing.
So, salt wasn't there. We have an acid
Mhm.
and we had an alkali. They reacted, so salt is prepared. Do you get it?
Yes.
So, preparation and separation are two different things.
Okay.
Do you get it?
Yeah.
Are you sure?
Yeah. So also alkenes are separated by cracking? I mean prepared by cracking.
Yeah, you just are too challenging. So, alkenes are prepared by separation, cracking. They are not separated by cracking. Do you get it?
Can you like write on the board so like I
So
like
that's your main
understand?
problem. Yeah, that's your main problem. You just don't think. You just need to write everything. You're not thinking. You're into reading. When I'm writing, you're just reading. You're not understanding. And when I'm explaining, you want me to write. You're not thinking. So just relax. Just understand. You cannot mix this up once that is very much clear in your mind. So far, we have discussing what? We have been discussing separation is something else and preparation is something else. You get it?
Yeah.
So if you are still confused, ask questions so that I can help you in that again. So when you say you're separating something, thing is already there. You're only separating it out from something. But if
Yeah.
you say you are preparing something, that means it wasn't there initially. You are preparing it from something that wasn't there. You are preparing it out of nowhere. Do you understand this?
Yeah.
Okay. So first thing is preparation of alkenes can be done through cracking. Like alkanes, we can prepare alkenes through cracking. So if we are, for example, having decane, let's write example decane, it can be converted into pentene and pentane. So I'm writing this equation to help you understand that cracking can help us to prepare what? An alkene. It can also be helped us, helping us to prepare an alkane as well. Do you get it?
Yeah.
Okay. Second thing, we can prepare alkenes from alcohols. You know what that was? We did this and you should have done this in O levels. Dehydration of alcohol. Now let's understand what this that has to mean. First, understand dehydration. What is dehydration? Dehydration is removing or removal of water. When you say you feel dehydrated, that means you need water, right?
Yes.
And then what's an alcohol? Alcohol is anything with OH in chemistry. So whenever we see OH, we have to refer an alcohol. Do you get it?
Yes.
So if I'm having an alcohol, let's do an example. This is an alcohol. Okay. Why is this an alcohol? Because we can see OH. So that's essentially ethanol, the correct name and the generic name for the functional group alcohol. Do you get it?
Yes.
And there are many techniques to, dehydrate it. Many techniques. Let's do only one. We can use concentrated sulfuric acid. You have to memorize it. And you have to maintain a temperature of 160 degrees Celsius to 170 degrees Celsius. And then it dehydrates. Now, what does that have to mean? It dehydrates. So dehydrates means what? You take water out. What is water? Water is H2O. How is H2O formed? Using H and OH. So do you see OH? Yeah, I can see it here. Do you see H here? I can see it here. Just take one H and one OH. So it is going to form H2O, and alongside it was supposedly CH3. So if you remove one H, what's left? CH2. And if you remove OH, what's left? CH2. So that's an alkene or ethene. Do you understand it?
Yes.
Take your time and then tell me. Do you understand it?
So basically, dehydration is removal of water, and you just remove H and OH using sulfuric acid, and there's this condition you use, and you get hydrogen and an alkane or an alkene.
We get water and an alkene. Yes.
Yeah. Is it always alkane plus alkene and alkane plus hydrogen, right?
Where have I written alkane and dehydration?
No, I'm just saying like whenever we do the cracking, we get an
Are you
alkane
talking
plus.
about cracking or are you discussing dehydration?
Oh, sorry, I was talking about cracking.
Yeah, yeah, okay. So in cracking, what are you saying?
Like you always get an alkane and an alkene, right?
No, no, not necessarily. You might get up all the alkenes, you might get up all the alkanes. So in cracking, we can have an alkane, all alkanes, we can have an alkenes, all alkenes. We might get a mixture of both of them. We might even get simple hydrogen. So what
Okay.
you need to learn or understand is cracking can help us make an alkane as well as an alkene. It's not always be an alkane and always be an alkene. No, it's not like that. It can be both, it can be only one.
Okay.
And for dehydration, we are going to get water and an alkene always.
Okay.
Through dehydration, you never get an alkane. So tell me this thing, have you done this previously
Yeah. Yeah, I have.
and you have done the same condition, sulfuric acid, or you have done something else?
No, I think I have done the same one.
That's so if we say that there is another procedure for dehydration, so that dehydration is going to be done with aluminum oxide, that's Al2O3, and then a high temperature is needed, 300 degrees Celsius, so it forms an alkene and water. So everything stays same, just this has been changed. Okay, you get it?
Wait, what? Can you say it again?
So everything stays same, it's just the condition that is changed,
This is the same reaction.
but with a different condition.
Oh, okay. So you can have both the condition, like.
Yes,
Okay.
you can have this and that.
Okay.
So do you understand it?
Yeah, yeah.
Any questions?
No.
Okay. We have just discussed how we're going to prepare an alkene. So alkenes are also prepared through different methods, but I think they are not in your syllabus. Am I right? Can you go through your syllabus and let me know if I'm missing on anything?
Um, they like the reactions they have given is the addition of hydrogen using nickel, the addition of
That's
halogens to.
basically not preparation of alkene. You just need to understand when I'm saying preparation of alkene, I'm preparing an alkene. So my product is going to be an alkene. If I'm asking or discussing reaction of an alkene, so reaction of an alkene is going to be my reactant being an alkene and then having something else on the product side. Right now, we are not doing chemical reactions of alkene. These are not chemical reactions of alkene. These are the reactions which help us obtain an alkene. So that's preparation of alkene. Preparing alkene is not anything relevant to chemical reactions of alkene.
So like, what are the other like ones you're talking about? So I can like say.
I'm just asking if you have done anything you recall in your memory in school under this concept, preparation of alkene. Just let me know. I'll explain that to you because I have, when I do this with my students, I have around 11 different techniques to prepare alkene. We have just done two.
There's this one like we did, which was electrophilic addition of bromine hydrogen to ethene.
Yeah,
Is
so
this
that's
also
not preparation of an alkene. That's the chemical reaction of an alkene. That is going to be discussed later on.
okay? Fine. Good. Nothing
So
else, I guess.
if you see topic 5 in your syllabus, it says know the general formula of alkene, right? We have done that and understand that alkenes and cycloalkenes are hydrocarbons which are unsaturated. So cycloalkenes we have not yet discussed. We are going to discuss that later on. Be able to explain geometric isomerisms and then we are discussing isomers and all, and then reaction of alkenes, right? So they never say addition polymerization is there, chemistry, yeah. So they never say anything other than this. Okay, that's fine. So now we can move on to chemical reactions of alkene. That's the main part of the topic. So so all alkene they go or they do electrophilic addition reaction. That's very important to know. So there are two keywords which are to be discussed here. First one is an electrophilic, and the second one here is the addition. So now I want you to tell me what do you understand by electrophile? What is electrophile in your understanding? Just
Is
explain
it
me,
when,
don't define it. Yeah.
is it when it accepts the like number of electrons, like attracted to the number of electrons, something like this, right?
So
Like
electrophile is anything, any
electron
species
accept.
that loves an electron.
Mm,
So electron loving is an electrophile. So it can be a cation, it can be a free radical as well. So anything that just wants an electron is an electrophile. That's very simple. You
okay.
get it? You get it?
Yeah, yeah.
And then it has to be electrophile doing some addition to it. So that's very important. So electrophile is, we have discussed, electron loving. Addition means we are going to add something to an alkene. So if we had an alkene, we are going to supply something to it. So that something is being added to it. So what do I mean by that? So let's do a general reaction. That's an alkene. It can be ethene, it can be propene, it can be butane, it can be any alkene. So reason I'm not writing anything here is it can be carbons, it can be hydrocarbons, it can be hydrogen, it can be lots of carbons, anything. But it would be an alkene, right? Because it has a double bond. You get it?
Yeah.
Okay. So now what they do addition reactions. So they are going to add something. So let's write AB.
Yeah.
These are, two substances which can be added to it. So what do we have in the product side? A and B being added, two carbons. So what they've done? They've done addition. Do you get it?
So yeah. So like, what about the? Wait, can you give like an example with like,
Yeah,
for example?
I'll explain everything. Don't worry. You just answer me. Do you get this reaction?
Yeah.
Is it showing addition?
Yeah.
Okay. Don't worry about your syllabus. Don't worry about the relevant exam. Just go with the flow. Do you understand
No,
it?
I was asking about the, how would the, like you said it would react with like cations or like a free radical. So why didn't you put free radical at A and B? Like,
I was explaining electrophile can be a cation or it can be a free radical. So
okay.
electrophile can be a cation, it can be a free radical. It has nothing to do with basically the chemical reaction. Electrophile is something we have discussed. That's it. Now the reaction is here. That's the reaction. Now, how is it an electrophilic addition? That needs to be discussed and that needs to be treated separately. So let's go take a deep dive into the mechanism of the reaction. So where this electrophile comes into play. So remember, the starting point for this mechanism has to be pi bonds. Now, first, you let me know that you are going to take a complete hour or you are just going to leave it right here. Because I cannot start if I don't have an hour.
Like 1 hour now.
Yes.
Um, can we do this part tomorrow?
Okay. Let's end.